going to section 2.6, if you follow along in your textbook, be very careful because Ms. Sackery teaches it in a little bit of a different order than Mr. Thomas. Okay, so I really have kind of reversed the way it was presented in the book by first going back and reviewing asymptotes, the horizontal, the vertical, and the oblique, and then doing the limits. And if you really look in the book, there's actually not that many questions on the limit. They ask an awful lot of questions on just tell me what the vertical asymptote is, tell me what the horizontal asymptote is, tell me what the oblique asymptote is, and then finally they ask you something about the limit somewhere in the middle of the homework set. So we're going to talk a little bit, we're going to really review you on these things that you might be a little rusty over before we jump wholeheartedly into the limit. And really, this is how it's presented in the book. It's just presented in a little bit of a different order. So limits involving infinity. So we're going to spend a little time here reviewing. Okay, reviewing asymptotes. This is a really unusually spelled word. Asymptotes. Now, also, with a little bit of concern by some of the expressions on your faces off and on so far this semester, when you have to graph a line, if it says x equals a number, this is a vertical line, right? Okay, this is the vertical line thing, where you're over here 1, 2, 3, 4 units, and that is your vertical asymptote. So if it says x equals a number, that's a vertical line. If it says y equals a number, like y equaling 2, this is your horizontal line. And you have to be extremely capable of this before we get in here and start talking about all these asymptotes. So y equaling 2 is the horizontal line up here. So when you have a vertical asymptote, you'll see graphs that do something like this, and boy, they'll come over here and they'll hit that vertical line and they'll shoot. They'll either shoot to positive infinity or negative infinity. When you see a horizontal asymptote, you may have a graph that'll come up and hug it like this, and then your graph will just stay horizontal along with the asymptote. So you will see your graphs hugging these asymptotes, whether they're vertical or horizontal. They will hug the line as they approach them. So reality is if you were way out here at positive, well, if you were headed toward positive infinity, your line would look like the horizontal asymptote. Okay? If you kind of blinded yourself to only looking out here at this part of the graph, your graph and the horizontal asymptote are going to look the same. So your graph kind of becomes the horizontal asymptote. All right. So now, let's talk a little bit about these lovely asymptotes. Okay. You guys know, no doubt, about these vertical asymptotes at this point. We've been doing a whole bunch of this. And that VA, I'm sorry, that's always my shorthand for the word vertical asymptote, which takes forever to write. But you know that your vertical asymptotes occur when the denominator becomes 0. Okay, we've done a bunch of this. You're good at this. This is something that's very fresh in your mind because we've dealt with this a lot already. So when you see a graph like this one, y equaling, say, 1 over x squared minus 9, you know that 3 and negative 3 are what causes the denominator equals 0. And we normally come in here and factor this, which makes it a little more visual then to actually see that the 3 and the negative 3 are the vertical asymptotes. Well, a vertical asymptote is an equation of a line who has only the x variable. So the equations of the vertical asymptotes are x equaling 3 and x equaling negative 3. Those are not solutions. Those are actually equations of vertical lines. So if you were to sketch this, then you go 1, 2, 3. Here's one vertical asymptote. 1, 2, 3. Here's your other vertical asymptote. And the names of those vertical lines are truly x equals 3 and x equals negative 3. Those are equations of those vertical lines. Then you say, well, I wonder what in the world this graph looks like. And so we normally pull up the calculator and type this in, which is fine. It's fair game. And if you do that, you'll see something like this going on. pretty wild graphs. Okay, back before we had these calculators, we would sit down and literally make T-charts, tables, and just keep throwing X values in until we had a vision of what these graphs look like by literally plotting individual points. So your calculator is heaven sent. Now, let's talk about horizontal asymptotes. Okay, there's two ways of coming up with a horizontal asymptote, but it has to do with the degree of the numerator and the degree of the denominator. Now, if you have an example like y equaling x over this x squared minus 9, then the degree of the numerator and the degree of the denominator is truly pretty much the exponent on the x variable. Now, it varies as you get into a more complex equation, but that's kind of the way it works here. So the degree of the numerator is 1, this 1 exponent on the x, and the degree of the denominator is 2. So if the degree of the numerator is less than the degree of the denominator, then you're going to have a horizontal asymptote, which is equivalent to the x-axis, which is called y equals 0. So if the degree of the numerator is less than the degree of the, and I ran out of space, of the denominator, if the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote at y equaling 0, which is the x-axis. Now we also know from the prior example that we also have vertical asymptotes at x equaling 3 and x equaling negative 3. So we have 3 asymptotes to this graph. 2 of them are vertical and 1 is horizontal. So if you were to graph this, instead of actually making a solid line from my x-axis, it would be appropriate to make it dashed because this is now your horizontal asymptote. Then you have an asymptote at negative 3, 1, 2, 3, and another one at positive 3, 1, 2, 3. And then I would pick up my calculator and graph this, and when you do, it looks like this. It's different from the one above. It looks like this. Now, if you look in the middle segment of this graph, we actually cross that horizontal asymptote. And you can. Okay, you don't cross vertical asymptotes, but you can cross a horizontal asymptote. You can. It's possible. But you can see where it's not crossing it is out here toward negative infinity, and out here toward positive infinity is where you're not crossing the horizontal asymptote, but it sure is crossing it right there in the middle. Looks like it's crossing it right at the origin. Okay. Now, just another thing, remember talking about end behavior somewhere in your past of your life in algebra? If you were to zoom back from this graph and extend it, okay, the ends on the left and the right, okay, if you backed out, I mean, if I held it up and you had really good vision from way back in the back of the room, the graph looks just like the x-axis because here it's hugging it and here it's hugging it. There's this small little world right in the middle of the picture that creates all this weird stuff. But the rest of the world, when you're going out to negative infinity and positive infinity in the horizontal direction, this graph looks just like the x-axis. So don't lose sight of the whole picture because we're focused so hard on this little part in the middle. Okay? So if the degree of the numerator is less than the degree of the denominator, then you have a horizontal asymptote at y equaling 0. Now I'm going to put a part B underneath this 4. Still talking about horizontal asymptotes. Where is the top of my piece of paper? There it is. Okay. So suppose you have a situation now, we're still talking about horizontal asymptotes, where, okay, still horizontal asymptotes, where you have something like this. Suppose your equation is y equaling 3x squared plus 5x over 6x squared minus 3x plus 6. Now, in this case, the degree of the numerator is 2, and the degree of the denominator is also 2. What happens when the degrees are the same? There you go. The horizontal asymptote is the coefficients, what they call the leading coefficients of the numerator and the denominator. So the horizontal asymptote is y equals 3/6 or y equals 1/2. So when you graph this one, the way it looks, you have a horizontal asymptote right here at 1/2, and it, let me see if I got the right one on my page, it looks something like this. Okay, so in negative infinity, it's hugging it underneath it, and on the positive infinity, it's hugging it above it. It does cross it. And it can, and it does cross it. So there's two types of horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, the y equaling 0 x-axis is your horizontal asymptote. If the degree of the numerator equals the degree of the denominator, your horizontal asymptote is to form that fraction of the leading coefficients of the numerator and the denominator. Okay, so just kind of you got to keep that solid in your mind. Okay, now part 5. Part 5 is what we call the oblique asymptote. The oblique asymptote. This would be an example of such an oblique asymptote would be this rational. In this rational, the degree of the numerator is 2, and the degree of the denominator is 1. So in other words, the degree of the numerator is bigger, right? The degree of the numerator is greater than the degree of the denominator. Anybody know about what to do now? This is where, to find your oblique asymptote, you use what we call long division. I bet this has been a while since you've done long division. Okay, that's not hard. Long division is to take x minus 1 and to divide it into x squared plus 1. But we don't go into x squared plus 1, we go into x squared plus 0x plus 1, which we refer to as complete standard form of the equation. So instead of x squared plus 1, we put x squared plus 0x plus 1. So we add another, like, place value term and throw a 0 in front of it. Then we say, how many times does x divide into x squared? Well, it goes in there 1x times. Then we multiply through times x. We say x times x is x squared, and x times negative 1 is a negative 1x. Then when we divide, we really subtract, or in algebra we call it change the signs and add. So we change the signs and add, and the x squared minus x squared is no x squared, and the 0 plus 1x is 1x. Then we bring down the plus sign and the 1. And then we say, how many times does x divide into 1x? And x divides into 1x a positive 1 time. So we put plus 1 up in the divisor. And then we distribute through by the plus 1 that we just put up there. So we say 1 times x is 1x, and 1 times negative 1 is minus 1. The operation is subtraction, which in the terms of algebra we say change the signs and add, and you get a remainder of 2. So, once you've done this, you have an oblique asymptote. Your oblique asymptote's equation is y equaling x plus 1 plus the remainder over the divisor, which is 2 over x minus 1. 2 over x minus 1. So that is the equation of your oblique asymptote. Now, when you're playing with oblique asymptotes and x gets exceedingly large, like x gets to be infinity, this becomes 2 over an extremely large number, 1,000,000. 2 over 1,000,000 is like 0, right? 2 over 1,000,000 is like nothing. So this is like 0. So as x gets extremely large, we say this really kind of goes to 0, so we can kind of eliminate that remainder. Yes?
Can you go through that process one more time?
Of division, of long division? Yeah, let me write this down one more time. Let me get this written. We'll come back, but let's get this, so far let's get this, okay, and then we'll come back and we'll do another example of long division. I think I got another one up here. Yeah, I got another one. We'll do another one, okay. So let's kind of stay focused on what are we doing. We're looking at asymptotes, and we just figured out the equation of the oblique asymptote, and there it is. This is your oblique asymptote, the equation of your oblique asymptote. So here's what I'm trying to graph, this big old ugly x squared plus 1 over x minus 1, which didn't look any worse than anybody else that we've done so far. But it kind of is. Now, if we look at this one, we have an oblique asymptote of y equaling x plus 1, and we also have a vertical asymptote of what? Of x equaling 1. So we have two asymptotes, the oblique and the vertical. So I wonder what in the world this thing looks like. Well, if you were to graph it, and I would definitely use my calculator, I have a vertical asymptote at x equaling 1, and I have an oblique asymptote y equaling x plus 1, which would look like this. There's your oblique asymptote. Okay? So here's your oblique asymptote, y equaling x plus 1. Here's your vertical asymptote of x equaling 1. There's your two asymptotes. And you can cross an oblique. You're not going to cross a vertical, but you can cross an oblique. And if you graph this one on your calculator, it's going to look like this. It doesn't cross the oblique. It's going to look like this. It's going to be up here and down here. And that's what the graph of that rational looks like. Pretty weird looking, right? It's been a while. You've done this before, I promise you. You did this in college algebra. But that was quite a while back. Okay. Before you took trig and before you took pre-cal, you took college algebra. And you did all this lovely stuff. Okay. So y'all want to do another one like that? Okay, so 5A, now we're going to do 5B, and do another one, another oblique asymptote real quickly. Get y'all kind of a little warmed up to the thought. 5 part B. Okay, let's do this one. Let's do y equaling, oh, this is a little harder. This is a good one, though. X squared minus 1 over 2x plus 4. Okay, right now they're just going to ask you to graph it, and then they're going to ask you to do the limit. And what's really weird is in this section, they're not going to ask you to limit very much. They're really pushing just to get you to graph the thing. Okay, so they're going to really just ask you to graph it. So when I look at this, I note that the degree of the numerator is 2, and the degree of the denominator is 1. So instantly, if the degree of the numerator is bigger than the degree of the denominator, then I have an oblique asymptote. And in order to get the oblique asymptote, I have to use long division. So long division is 2x plus 4 divided into x squared minus 1, which I rewrite as x squared plus 0x minus 1. To do the long division, you need that 0x in there. And this is interesting. How many times does 2x divide into x squared? Does anybody know? 1/2 x. X squared, 2x divides into x squared 1/2 x times. So I put a half x up here, and then I multiply through. 1/2 x times 2x is x squared, and 1/2 x times 4 is 2x. So I multiply through 1/2 x times 2x and 1/2 x times 4. Then I come in here and I change the signs and add, which leaves me a negative 2x, and I drop down the minus sign, and I drop down the 1. Then I say, how many times does 2x divide into a negative 2x? Negative 1 times, which I write as a minus 1, and then I multiply through by the minus 1, which gives me a minus 2x and a minus 4. And don't forget to change the signs and add, giving you a remainder of 3. So this x squared minus 1 over 2x plus 4 actually becomes y equaling 1/2 x minus 1 plus the remainder over the divisor, which we're going to refer to as our oblique asymptote.
Why do you switch the sign?
Yeah. When you take 4 into 27, it goes 6 times, and then your operation here is to subtract. Remember? So that's what we're doing when I'm using the pen. Now, when you're looking at limits of infinity, you're looking out in the infinite direction. If x was infinity, this would be a huge number at the bottom of the fraction. And 3 over a huge number is like 0. So we claim that this is kind of headed out towards 0. We kind of actually knock it out of the picture. And we just look at the 1/2 x minus 1, and this is my oblique asymptote, which is really what my function kind of turns into at the infinite ends of the world, to the left and to the right. Okay, so this original rational has an oblique asymptote of 1/2 x minus 1. And when you also look at this, you have a vertical asymptote also, right? What's your vertical asymptote of this rational up here? X equaling -2. Okay, so if we really want to graph this, we have x equaling -2 as a vertical asymptote over here. And we have this oblique asymptote of 1/2 x minus 1. Something like this. Okay. And when you graph this one, and I might should put this on the calculator to give y'all a little, I hope y'all are comfortable with graphing this on the calculator. Let me put this on the calculator so you can see it on the calculator. This is what you're graphing right here. Your original, what you're graphing. When you pull up the calculator and you graph this thing, it's going to say y equaling x squared minus 1 divided by 2x plus 4. Alright, and so we're looking at -2. I'm going to do a zoom. I'm going to do a zoom decimal, I think, on this one. And there it is. See it down here? There's your graph. I did a zoom decimal on it. So it looks like this. So just kind of getting comfortable with these rational functions. You have horizontal asymptotes where the degree of the numerator is less than the degree of the denominator, and the horizontal asymptote is y equaling 0. You have horizontal asymptotes where the degree of the numerator equals the degree of the denominator, which gives you a horizontal asymptote equal to those leading coefficients, that fraction of the leading coefficients. And then you have, when the degree of the numerator is more than the degree of the denominator, then you come up with these lovely oblique asymptotes, so that now you should feel covered. You should be tired of asymptotes. All right, so now you should feel pretty good about all this. All right, so now that we're like overwhelmed with asymptotes, let's move over to part B. And let's actually look at a definition in the book on page 86, which is actually defining a horizontal asymptote. And it doesn't hurt to kind of look at the book periodically to make certain that y'all feel comfortable. Listen to that southern accent. Y'all feel comfortable. That you are comfortable with how it reads, how it is written algebraically in this pretty little expensive textbook. Okay, here it is. There it is. A line y number is a horizontal line. Y equaling b some number is a horizontal line. Asymptote of a graph of a function, y equaling f of x, if either the limit of x's approaches infinity of f of x is b, or the limit as x approaches negative infinity of f of x equals b. Study that for a minute. Think about it. Ponder if you understand what it means. Okay. And then I'm going to also write it down just a little bit. Okay, so what it says is if y equals b, if this is a horizontal asymptote, if we're claiming y equals some number, some horizontal line, being a horizontal asymptote, then the limit of some function as x is approaching infinity must equal b, or it can be in the negative infinity direction for our limit. So in other words, if we apply this to an example, if we kind of come out to an example, suppose our function is 5x squared plus 8x minus 3 over 3x squared plus 2. Now, that function has a horizontal asymptote. What is it? 5/3, because the degree of the numerator is 2, the degree of the denominator is 2, the degree of the numerator and the denominator are the same, so you take that ratio of those leading coefficients, and that is your horizontal asymptote. That is your horizontal asymptote. So, by this definition, we would say the limit of this f of x, this big old 5x squared mess, as x approaches infinity, is b, where b is the number 5/3. Or the limit as x is approaching negative infinity of this f of x is 5/3. This is an application of that definition of a horizontal asymptote. Okay, that's a definition where y equaling b is like y equaling 5/3. This is the letter b in the definition. Are you doing good? It's been a while back, but I kept saying, we're going to find the limit, we're going to put on this piece of paper that the limit of f of x is x expressed as a number is infinity. And when I wrote it, I was a little bit uncomfortable with writing it because I said infinity is really not a number. We really don't have the right to do this, but we're going to do it anyway. Well, the book is just now approaching that fact that a limit is supposed to be a number. But we kind of are crossing the line here and permitting the limit to equal infinity when infinity is really not a number. So, for example, this is what we've been doing. If we've been taking something like the limit of 1 over x as x is approaching 0 from the right side, remember what 1 over x looks like? Looks like this. Okay, this is f of x equaling 1 over x. So when we say the limit as x is approaching 0 from the right side, what do? It equals what? Positive infinity. And so then the book says, this is an interesting thought. Let me see if I can find it in the book now that there it is on page 89. So they finally come in here and make a statement. It's on page 89. they're doing this very thing we just did. And as x is approaching 0 from the right of 1 over x equals infinity. And then they say, wait a second, I better be careful. In writing this equation, we are not saying that the limit exists. Nor are we saying that there is a real number infinity, for there is no such number. Infinity is not a number. Okay? So they're covering themselves here. Rather, we are just saying this limit really does not exist because 1 over x becomes arbitrarily large and positive. So really, this limit honestly does not exist because it's not equaling a number. And they're just now finally saying it. And this is the only place they're going to say it. So we're going to continue to write infinity, and in reality, the limit honestly does not exist. Okay, so be very careful. And then they do it again here, because if we were to take this limit as x approaches 0 from the left, it would be negative infinity. And again, they're saying, we are not saying that this limit exists, and we're not saying that it actually equals the number negative infinity, because there is no real number negative infinity. We are just describing the behavior of the function. Right? So kind of keep that always somewhere in the back of your mind, because it's possible that you'll run into a professor that will eat your test fast when you answer it with infinity rather than saying it does not exist. Now, I would not do that, and most instructors would not, but you better pay attention to the professors you have in the future, because they would have the right to do it based on what that textbook says right there. Okay, so you've got to be very, very, very careful. Now, let's go ahead and take a break for a minute before we actually go a little further. I'm going to pause this recording.